combined gas equation. It's a combination of Boyle and Charles' law. So we know that P1 V1 is equal to P2 V2, and V1 on T1 is equal to V2 on T2. Well, we can combine that together, and we can see that P1 V1 on T1 is equal to P2 V2 on T2. And this is the combined gas equation. And so, one gas, two conditions. This is important. And even if you just remember this one, it's going to work anyway, isn't it? So if you, it doesn't matter which variable is constant, it's going to work out okay for you to solve all your combined gas equation questions. So let's have a look at the example on page 17. It says that some helium gas is at a temperature of 10 degrees Celsius. So we've got T1 is equal to 10 degrees Celsius. We're going to have to change that. So it's going to be 10 plus 273 is 283 degrees Kelvin. It has a pressure of 100 kilopascals, so P1 is 100 kPa, and it occupies a volume of 3.20 litres. V1 is equal to 3.20 litres. To what temperature in Celsius? So here's another, I guess, trick, if you like, or a place where you can make a mistake, is that there is this expectation that your answer will be in the same units as the question was asked. And so we were given the temperature in Celsius, we have to give our answer in Celsius. So to what temperature in Celsius must it be heated in order to double its volume? So with volume is going to be 6.4 litres, and the pressure is 120 kilopascals. Alright, so we're going to use this relationship here. We're finding T2. Right, so to find T2, we've got a bit of rearranging to do, don't we? We're going to have to, it's going to end up there, that's going to end up there, and these two are going to end up there. So T2 will equal P2 V2 T1 divided by P1 V1. You all right with rearranging like that? We can do that slower if you want. We want T2, so, but you don't have to do it this way either. You could solve it. You could solve this as a, and get the numerical value for that. Then divide this by your answer. But anyway, let's continue on. T2 equals P2, which is 120, times V2, which is 6.4, times T1, which is 283, divided by 100 times 3.20, which gives us 679 Kelvin, apparently. And then, to find our answer in Celsius, we're going to have to subtract 273. 406 degrees Celsius. So if I look at finding, if I want T2, P1 V1 on T1 is equal to P2 V2 on T2. To get T2 from the bottom, I'm going to multiply both sides by T2. They cancel out, and what I have then is P1 V1 T2 divided by T1 is equal to P2 V2. So now I'm going to multiply both sides by T1. They cancel out, and I've got P1 V1 T2 is equal to P2 V2 T1. And now I'm going to divide both sides by P1 V1. And then they cancel out, and I get T2 is equal to P2 V2 T1 divided by P1 V1. Okay, so that was the algebraic process that I just sort of did there with those arrows. But like I said, if you're not comfortable with that, then you can follow along the working in the booklet that's basically solved this side first and got a numerical answer for it. And so either way is fine, whichever way is most comfortable for you. And then there's a nice page of questions on the combined gas equations on page 18.